Tak ještě jednou dobrý den. Já bych vás chtěl všechny přivítat a poděkovat, že jste přišli na dnešní webinář, který bude celý v angličtině, protože tady společně s námi, s Techsoftem, jsou i dva zástupci společnosti ANSYS, Greg a Shin-san. So I will switch to English from now. So thank you very much, everyone, for coming for today's webinar. We planned it for like an hour and something. So I hope you will stay with us. So at the very beginning, I would like to introduce to our colleagues from ANSYS UK, which is Greg and Shin-san. So these guys have been with Lumerical, now ANSYS, for more than 6 years on several application positions, and also Shin-san is now a manager of application engineering at ANSYS. So these are the guys who will go with you today with the presentation. So this photonic stuff it's quite new to ANSYS. I think the Lumerical was acquired like a year ago or so. So, and it's also quite new for Czechia and Slovakia, and it's somehow connected to our optics business, which we do as an ANSYS Allied channel partner in Czechia and Slovakia, and helping some other channels within the Eastern Europe. So at the very beginning, I would like to tell a few words about Techsoft engineering. So I will present some company presentation, but will be very short. And then I will give my word to the guys, and they will follow with the numerical stuff. So as a Techsoft engineering, we are doing is we are selling and helping companies with virtual prototyping. So we want to have to shorten your cycle of the product development. That means also the reduction on the cost. So you don't need to make many physical prototypes and follow with the testing. So you are able to handle that in a virtual on the computers. So it will make you more beneficial and less time consuming for the product development. So you can produce new products, or you can develop your current products to perform better. As a company, our main scope is to deliver license to you and do some complementary services like trainings and product support. That means that we want to bring you our know-how, how to handle with ANSYS products, and to be really beneficial to using that from the very beginning very efficiently. That means we are also able to do some outsourcing. We are doing some seminars and conferences or webinar like today. And we are doing partly also on some software development, that means customizing some GUI and things like that to really perform and do a quicker simulation also for a non-professional users at the end. So we are on the market since 1991. So we are currently 26 people at Techsoft Engineering. We started with ANSYS Science. ANSYS acquired a company called Fluent, and it was in 2006. So from that time, we started to be ANSYS partner. Nowadays, we are ANSYS certified allied channel partner for Czechia and Slovakia. So since 1991, we performed many projects on the benchmarks for our clients, and we have more than 200 of customers. We are currently placed in Prague. We have a subsidiary in Zlín on the eastern part of the Czechia, and we also have some cooperation with company Techsoft Engineering Slovakia in Košice. So we are spread all around these countries. Our main intention is to bring all ANSYS portfolio to Czechia and Slovakia. That means that we are the only partner who is covering all of the parts of ANSYS portfolio. Of course, everybody knows fluid structure and electronics. Then since 2019, we are also operating with the optics, which Lumericals is somehow a part of that nowadays. We are able to help you in the development or testing of semiconductors. We do some system analysis, 3D design with ANSYS Discovery, and we also are able to deliver software for critical embedded software simulation, or coding. So that means that you can also make some codes with us. At the end, it's like also we do have a material database called ANSYS Granta. And since 2020, we are also cooperating with a company called PTC, which is also a partner of ANSYS. and we are cooperating on the fields of augmented reality and IoT. So these are the parts of Ansys portfolio and PTC portfolio that we are able to help you with. So nowadays, it's also more important to be connected somehow with us. So where you can find us, of course, we have web pages. Besides that, we are also active on Instagram, Facebook, and LinkedIn. So if you can, please connect. If you want to stay with us, please connect to us. So this is a photo of my colleagues. And the last word I want to mention is that the webinar will be recorded. That means we will provide you at the end with some links after some editing of the video. So you will be able to review everything. And if you want, we can also share you with a PDF file of the presentation we will present today. And during the seminar, we will also mention that there will be a questionnaire. So we want to share you with a link, so you feel free to fill it. So we will be able to somehow handle how we can perform it better. So and also in the case of questions, so you please raise your hand, or you can put a question in the chat. So we will review that and answer that when possible. So that was my part from the company perspective, Textsoft Engineering. And I would like to take over to Greg, probably.
Yep. Thanks a lot, Michel, for the introduction. Okay, let's see if this works. I'm going to share my screen.
Yeah, we can see you now.
Excellent. Not sure if it's a good thing, but okay. Can you see my screen?
Yes, we can. Okay,
thank you very much. So yeah, as Michel just said, I'm Greg Bedge. I'm a senior application engineer at Ansys Lumerical. I'm here with my colleague and manager, Shin-Sung Kim, and we both have been working for Lumerical for quite some time now. My background is on the photonics side, but you will see that Lumerical application range can extend a bit further than just the light behavior, and so I'll definitely try to tell you about all these what Lumerical can do and how it can help you with photonic simulations. So as Michel said, feel free to post your questions on the chat. I think Shin-Sung will keep an eye on that and eventually answer. Other than that, I mean, I'll hopefully we should have some time at the end to answer some of your questions. So for this this presentation, I'm going to go basically over like introducing Lumerical, Ansys Lumerical to you, and then I just want to talk about the different solvers that we have at Ansys Lumerical, and also I want to go over some of the applications that we target for these solvers. So Lumerical, as Michel said, Lumerical is actually fairly recently acquired by Ansys. Actually, the acquisition was in April last year. But initially, Lumerical was a Canadian company based in Vancouver, and actually most of our team is still based in Vancouver, while Shin-Sung and I are based in UK. So the aim of Lumerical was simply to try and provide the best photonic design tools for engineers. So why that is simply because the founders of the company were themselves engineers, and they found in the early 2000s that there wasn't any simulation tools that were good enough, or at least fulfilling all the needs that they had back then. And coming from that, they started developing their own tools. And the main tools that the first tool that they actually developed was FDTD. So FDT back then was called FDT Solutions, and that was the first commercial product that came out in 2004. And through the years, from the inception of the company to its acquisition, and actually still now, we've always focused on our customer success. And so what we tried to do over the years was simply to improve the products, but also widen the range of solvers in order to enable simulation workflows in the photonics field. So why that? Why photonics is important? Well, photonics in a way is everywhere nowadays, in consumer products or in industrial things and so on. So let's talk about some of the applications where you can find photonics devices. So in smart homes, you will see photonics in like ultra high definition televisions, smartphones, like the CMOS image sensors on your camera, can be LiDARs and so on. There's the whole development on Internet of Things, sensors, virtual reality, augmented reality that use photonics devices. We have the same kind of application in the industrial field with industrial augmented and virtual reality devices, machine vision, laser processing, and so on. In infrastructures and security, LiDAR is widely used, especially if you think of autonomous vehicles. Then we have optical communication, sensors, lighting, displays, solar energy that use the photonics devices. In healthcare, all the work on medical imaging, diagnostic, lab on a chip, and again, augmented reality can help for enhanced surgery systems. And one of the fields that probably had a huge impact over the past 20 years also in the photonics world is data center and optical telecommunication, where the race to get the higher bandwidth, the fastest internet, and with the lower cost and lower energy consumption, led to the developments and the increase and a lot of work in the development of optical transceivers, optical storage, and so on. So all these are kind of like different applications or different fields where photonics devices can be found, and all these different domain definitely pushed the development of simulation tools such as the ones we provide at ANSYS Lumerical. So in terms of the tools that we provide, there's simply we can split them in two categories. The first one, which is more where Lumerical comes from at first, is the component level simulation tools, where what we are interested in is simply the physics of what is happening in your device. So they're optical solvers. There's also other solvers that will detail in a short bit. So again, here we are talking about a physical device, and we're solving the physics that are happening in this device. And on the other hand, we have the photonic integrated circuit side, the circuit and system level side. In this case, we're not really looking at the physics behind all the different components, but the circuit, similar to what we find in the electronics world, each component of the circuit is described by a behavioral model. These models we'll see in a bit can be extracted from the component level simulation. But this way of working using a schematic view of your circuit allows to develop and design very complex circuit that can have tens, hundreds, or thousands of components, and then run the simulations and extract the characteristic of these circuits and optimize these circuits. So all these different tools share a common set of features. For instance, we have our own scripting language that allows you to drive the simulation workflow, create your structures, your simulation, run the simulation, and then extract the data to post-process and calculate whatever results you are interested in. And then we have an automation API available from a scripting language, but also from Python or MATLAB. The automation API simply was designed with the idea of being able to run multiphysics simulations. As we will see in the next slide, our tools cover multiple physics from the photonics side, but also electronic or thermal side of it. And when you're interested in simulating such devices, such complex simulation workflows, the automation API allows you to have one single script that will drive the full simulation workflow without having to open different scripts, running different simulations and so on. Or we still have to run different simulations, but everything can be driven from that one single script. Additionally, and based on this automation API, we have a photonic inverse design module called LUMOPT that allows the optimization of photonic integrated circuit components based on the Adrant method, and I will show a couple of examples later on. So all these features are simply shared by all of our products. So now on the component level side, we have these three packages. So where FDTD and MODE are basically the pure photonics simulation tools. So in these two packages, what we do is we simply solve the Maxwell's equation in order to see how the light can propagate in a structure. So FDTD is probably the most versatile of these tools. So FDTD stands for finite difference time domain, which is the name of the algorithm that we use to solve the Maxwell's equation. Again, it simply allows to calculate how the light can propagate, like in this CMOS image sensor simulation, and you see the fields propagating and being absorbed in a silicon layer. And so why it's so versatile is simply because there are no assumption or no I forgot the name. Anyway, there's no assumption about the geometry, the material that you're using, and so on. So it means it can be applied to a wide range of applications and devices from the moment you are interested in the propagation of light in the device, and the feature size of your device are about the same scale as the wavelength. And that is definitely, I would say, the common point of all our tools is in the photonics world, we are talking about devices where the feature size, the characteristic of the device are about the same scale as the wavelength. In this specific example, this CMOS image sensor, the pixel size is about 2 micron wide. And we have actually 4 pixels in our simulation for each of the primary colors, red, green, and blue. And you see that even though this width would be about 2 micron, we have features like bias and bias and so on that can be of a few hundred nanometer wide. And that's why we need to be able to solve the Maxwell's equation in order to take into account things like the diffraction and so on that can be caused by these elements. So on top of the FDTD solver in this package, we also have the stack optical solver. So the stack optical solver is a tool that can deal with multi-layer stacks, and it's simply using an analytical method to calculate, for instance, the transmission and reflection coefficients of the device using a plane wave illumination. Or if you are interested in simulating devices like emitting structures like an organic LED, for instance, where light is emitted from one of the layers, we can use a dipole illumination to characterize the stack and calculate the emission pattern of that stack with this illumination. Also, and it's common to the two optical solver, not solver, but the two photonics design tools, we have some interoperability with ray tracing software, basically going from the wavelength scale to the microscopic scale by exchanging data from one to another. So that's for FDTD. MODE is in a way very similar to FDTD. The only thing is that in this case, MODE is specifically designed for the simulation of a waveguiding structure. So we're talking about structures where there's waveguides, fiber optics, and so on. And so for these devices, we have 3 different solvers. The first one is a simple eigenmode solver. So the idea is you know the cross-section of your waveguide, and you want to characterize this cross-section and calculate what are the modes that can propagate in each structure. So you can extract things like the mode profiles, so basically the fields as a function of the position, but also other characteristics like the effective index, the group index, or the dispersion of that waveguide. Again, in this case, we're simply looking at the cross-section. And then we have 2 other solvers that can propagate the light in either a main direction or omnidirectionally, like in this device. So they have 2 different types of, or they apply to different types of structures. So the first one that is based on the FDTD method and is called the variational FDTD solver. or VAR FDTD. In this case, it applies to waveguiding structure, or let's say planar waveguiding structure. So in this case, the propagation of light is in a plane, and the thickness of your waveguide is constant, and there's no coupling in a vertical direction. So in this case, the advantage of this method is simply that we start from a full 3D structure, in this case, a ring resonator. And what we're going to do is we'll collapse that structure in a vertical direction and extract an equivalent 2D structure using a set of effective indices that are calculated by the solver. And then the simulation itself is run in 2D, which allows for faster simulations, but also allows larger simulations, since the larger the simulation is, the more computationally intensive it can be, especially if you're doing a full 3D simulation. So that's for the VAR FDT solver. And then we have the eigenmode expansion solver. So the eigenmode expansion solver doesn't have any assumption on the geometry of your waveguide, like the cross section. It can be planar, but it can also be non-planar, like a fiber. The constraint with the AME solver is that the propagation has to be in a main direction along the x-axis. But on the other hand, we can deal with very long propagation distances very efficiently. So in this device, this is called a multimode interference coupler, where we have one waveguide at the input, and we want to split the light equally to these two output waveguides. And so you see different sections in this device. We have the input waveguide, we have a taper leading to this multimode interference region, and then we have two output tapers and the output waveguides. So the advantage of the AME solver is that we can vary the propagation length very quickly. So might not be the best example here, but we could easily change the length of this taper coming from a few microns to hundreds of microns within seconds and get the results very efficiently. So as I said, there's also these tools also share the mode also share the same interoperability with ray tracing software, and I'll talk about that in a short bit. So that's for the pure photonics design tools. On top of that, we have the multiphysics environments. So why did we develop this multiphysics environment? It basically came from the realization that mode and FDTD can deal with a lot of devices, but if you want to model active devices like photodetectors or optical modulators, for instance, we have some limitations, and we need to be able to address other physics in order to fully model these active devices. And so we developed the multiphysics environment first with the charge transport solver. So the charge transport solver is there for the electrical simulation of semiconductor-based devices. So it's based on a drift diffusion and Poisson equation solver, and it will allow you to calculate the charge distribution and fields in a semiconductor device based on the doping profiles, bias voltage you apply on that, and so on. But the main thing when we developed this tool was that we are a photonics-based simulation tool provider. So we designed this environment to facilitate the data exchange from, in this case, the charge transport solver to the photonics simulation tools. So for instance, and I'll talk about that again later on, you see here a waveguide where we have a PN junction. So it's a silicon waveguide, and the doping are simply creating a PN junction. And we can apply a bias voltage sorry, on this PN junction and calculate how the charge distribution over the waveguide changes as a function of the bias voltage. And then we can extract this charge distribution as a function of the voltage and use that in the optical simulation for and include that as an index perturbation. And this allows simply to calculate how the properties of the waveguide will change when you apply a bias voltage. And that can be then used later on to create a phase shifter in a circuit simulation. So these go in one way, but the other way around is also possible. So if you look at the simulation of this photodetector, as I mentioned, the light is absorbed in the silicon layer, and what we can do is we can use that absorption calculated by FDTD in this case as a charge source in a charge simulation itself, and then we can extract the photocurrent that is generated by this device, this photodetector. So that's for the charge transfer solver. So as I said, this was the first solver that we included in this environment, and later on we added the heat transport solver for thermal simulations and the heat transport simulation in solids. And again, the idea is exactly the same. The idea is that we can exchange data from the multiphysics environment to the optical solvers. So we can use here the temperature map that is calculated by the heat transport solver. We have a heater here, we have a waveguide somewhere here, and we extract the temperature map and use that as an index perturbation in the mode calculation. And we do exactly the same as with the charge solver. We can calculate how the optical properties of the waveguide are affected by the temperature and the power you inject in this heater. And again, the other way around is possible. If we can use the absorption as calculated by the optical solvers as a heat source in your thermal simulation. So those are the two non-optical solvers that we have in the multiphysics environment. And on top of that, we have two optical solvers, DGTD and FEAM, that are doing photonic simulations. The one thing I forgot to mention is that where FDTN modes are based on finite difference simulation algorithm, so where we use an orthogonal mesh to discretize the geometries, the multiphysics environment is based on a series of finite elements solvers. So in this case, what we use is the structure is discretized using tetrahedral or triangles, depending if your simulation is in 2D or 3D. So these optical solvers that we have in the multiphysics environment are therefore finite elements solvers, and they're kind of the equivalent of what we have on the finite difference side. So DGTD is the equivalent of what FDTD is. So it's a Maxwell's equation solver in time domain, where we calculate how the light is propagating in your structure. And FEAM is an eigenmode solver, so calculating the mode properties of your waveguides, but again, using finite element mesh like shown in this fiber simulation. So on top of these four solvers, we have the multi-quantum well solver. So the MQW solver is meant for the simulation of laser material based on multi-quantum wells. So the idea is that you can calculate with this solver the gain curves of your multiple quantum wells, and use that to create a laser cavity in a circuit simulation. And so it includes different set of materials, and so it has some limitation in the type of semiconductors you can use for that. I won't go too much into details because that would be a bit too much. So that's for the component level tools. And as I mentioned, we have some interoperability with ray tracing softwares. So I will focus here on the interoperability we have with our colleagues from ANSYS Speos, but we also have some interoperability with other ray tracing softwares like Zemax, for instance. So in the case of Speos, since actually the acquisition of Lumerical last year, we saw quite a lot of synergies between the ray tracing and the wave optics simulation tools, and sometimes you need to be able to have a bridge between the two. And so here in this slide, you see a few applications that we had in mind, and some of them already led to some demonstration and proof of concept. So the first one we worked on was for head-up display, where so you see the result of a simulation by Speos, where we can simply calculate what is the actual rendering, what the end user will see on a windshield, based on the information like the materials, the coatings, and so on. So here, what we can do is we use a coding to reflect the display towards the end user, and this coding can be modeled using Lumerical. So we can use, for instance, the stack optical solver if this coding is simply multiple stacks put together with different thicknesses and materials, and you can extract the transmission and reflection coefficients as a function of the wavelength and as a function of the incident angle. So that's one way. And the other way, going a bit more with more complex structures, we can use plasmonic particles to reflect or transmit the light. So in this case, by playing with the shape, the size of these nanoparticles, we can create a reflective coating with a specific reflecting coefficient as a function of the angle. And so this can be done in FDTD, and we can extract the data as a coding file that can be imported in Speos, and then we can run the simulation and see how this coding would work in a display in a car. So that's one application that we thought. Another application, and I'll go all the way on the right, is a CMOS image sensor. So in FDTD, and I'll talk about that later on, when I will review the applications, we can characterize and optimize the pixels for this image sensor. But then this matrix of pixel can be used in a camera, and the camera includes multiple objects. So you have the optics, you have the matrix, and so on. And with Speos, we can actually model the full camera system, and using how the pixels can generate the image, we can go from the scene that you want to take a photo of, and generate using Speos what is the actual image that will be recorded by the camera. So that's another application that we demonstrated a few weeks ago, and the last one that we showcased in a recent webinar was for emissive structures like this macro LED. So the idea is that we can use an FDTD simulation or a stack, an optical stack solver simulation to extract the emission pattern of this emissive structure, and then use this emission pattern to build and simulate a full display like this, the screen of this mobile phone in this picture. So this is a simulation done with the Speos as well. So those are the three applications that we actually have demonstrated recently. And there's other type of applications that we are thinking of and we're currently working on, whether it's surface or volume scattering, where we can extract the BSDF from this surface with FDT and use that in Speos, or for diffractive optics, like this grading, where we can calculate all the different grading orders, the strength of the different grading orders, and then the idea is to use that in the ray tracing simulation. And this can be used, for instance, in applications like these lighting in a car, but also in like augmented or virtual reality applications. So that's for the interoperability with the ANSYS Speos ray tracing software. And that basically ends the part on the component level tools. So now we're going from the component level to the circuit level with Interconnect. So Interconnect is our photonic integrated circuit, or PIC simulation tool. As I mentioned earlier, in this type of software, we are not talking about solving the physics of what's happening in a circuit, because simply this would lead to huge simulation and it's not realistic to try and model that. So instead of using the full physics based simulation tools, what we do is we have a schematic view of the circuit, and each component of that circuit is represented by a compact model, a behavioral model. And these models can be extracted from the component level simulation tools, as I will talk about in a bit. And so what Interconnect can do is simply simulate these circuits in the frequency domain and in time domain. So in frequency domain, what we can extract will be the transmission spectrum of the circuit, and in the time domain, we are more interested in things like the signal integrity and extract like the eye diagram of the circuit. Additionally, Interconnect supports statistical analysis, so we can run corner analysis and Monte Carlo analysis. The idea being to be able to determine the yield, the manufacturing yield of your device, your circuit. So, as I mentioned, we need compact models in order to describe the behavior of these different components. And in order to help generating libraries of compact model, we developed a tool called the CML compiler. So the CML compiler is simply allowing to automate the generation of these compact models for Interconnect using simulation data, but also experimental data. So this is primarily designed for foundries or companies or groups that are developing, let's say, a fairly large library of components as part of a process design kit. Simply, in this case, the advantage of using a tool like the CML compiler is simply because you can automate this process, it's much easier to deal with multiple iteration of your process and different versions of your libraries, and makes things much easier for that. So as I said, the CML compiler will generate compact models for Interconnect, but it also generates Verilog models that can be used in the electronic photonic design automation flow that we have with our partners from Cadence. So in this case, we're using the Cadence Virtuoso environment to drive the simulation. I'll talk about that in a very short bit. And since these environments will use Interconnect or can use Interconnect as the photonics simulation engine, we need a bridge between the Cadence view of the circuits, of the components, and the Interconnect library of components. So this came up simply from a realization, and obviously we're not the only ones to kind of think about it. It's simply that there's a lot of similarities between what happened something like 50 years ago in the electronics world and what is happening now in the photonics and the integrated photonics world, with this idea of having a simulation workflow that is centered around the process design kits. So the process design kits will include all the information about the manufacturing process, the design rules, the process data, the layout of all the different components that are available in his PDK. And most important for us at NCS Numerical will be the library of compact model that will allow the simulation of these circuits using these models. But the first thing when we talk about a process design kit and a library of compact model is simply that you have to generate these compact models. And to do so, you need photonics multiphysics simulation tools like the ones provided by NCS Numerical, and also you have to be able to calibrate and characterize these components using measurements. And that's where the CML compiler can help in order to automate the extraction of the data from the component level simulations and the measurements to build these libraries of components using all these data. So once your library of components is ready, then that library can be used for the circuit design, the circuit level simulation using the process design kits. And so on this side, there's typically two ways of working. And funny enough, I think it depends a lot of what your background is. If you come from the photonics world, you will most likely be working on using a layout-driven simulation flow, where you will be using layout tools, whether it's commercial tools like TANA-Edit or open source tools like KLayout, and you will build the layout of your circuits using the different layouts, the masks, the GGS file from the different components, put them together and create your circuit. And from that, you can extract a netlist, and that netlist can be used in interconnect for the photonic simulation. And so you can analyze the performance of your circuits based on the layout that you generated. So that's one way to work. The other way that is more what people in the electronics world are doing is to start from a schematic driven simulation flow. So in this case, you're using a schematic capture of your circuit. That can be done in, for instance, Cadence Virtuoso. And in some way, interconnect is also a schematic editor. But using, let's say, EDA tools like Cadence or Mentor, now called now part of Siemens, is the fact that in your schematic capture, you can actually include the photonics side of the circuit, but also the electronic side of the circuit. So you have, let's say, drivers that are driving the optoelectronic components of your photonic circuit. And from that single schematic view of your circuit, you can extract two different netlists. One describes the electrical circuit, and one describes the photonic circuit. And in this simulation workflow, we have co-simulation capabilities where during the simulation, the two sides of the circuit simply communicate with each other. So for instance, you have your drivers with a sequence of bits, and it generates an electrical signal. This electrical signal is sent to the photonics part to feed the photonic circuit. And then on the other hand of the photonic circuit, you have a photodetector. The photodetector will generate a photocurrent, and that photocurrent will be sent back to the electrical circuit to get exactly what is captured by the circuit. And so everything is happening simultaneously in this co-simulation workflow. So once you've analyzed your circuits, you simulated your circuit, and you're happy with the performance of your circuit, then you can extract the layout and do the usual verification, design rule checking, and then do things like layout versus schematic, where you may have to modify your layout to make it manufacturable, and you want to check if these modifications affected in any way the behavior of your circuit, so you can get back to the schematic view and so on. And once you're happy with your design, you know it's manufacturable, then you can send it for fabrication to the foundry. So all this work is actually came from collaboration we've had over the past few years with different foundries all around the world. So coming from in no specific order, like AIM Photonics in North America, we have Fraunhofer HHI in Germany, IMEC in Belgium, Smart Photonics in the Netherlands, and so on. The latest collaboration we had that was actually announced a few weeks ago with Global Foundries. Now, all these different foundries work in various processes. So we have Smart Photonics using indium phosphide technology, while IMEC is using silicon photonics. So we definitely don't have any specific view on whatever material based you should use for your photonic circuit. It all depends on the type of applications and the needs you have. But we're simply there to support you and support the foundries so they have a library of components that can be used in interconnect for circuit simulation. So that's about it for the really the presentation of the product. Now, what I want to talk about is more like specific applications where our products can be used. So in this slide, we have a lot of different applications you can see. One thing though is that the first row of this slide is simply applications related to photonic integrated circuits, so PIC simulations, while the bottom row is more, I would say, anything outside of the PIC side of it. So for the photonic integrated circuit side, we have datacom applications, we have LiDAR, we have quantum photonics, process design kit development, as I just talked about, as well as sensors. And then we have image sensors for cameras, like pixel simulations, as I talked about. For augmented and virtual reality, we can do meta lenses, diffraction gratings, and display, like LEDs. These can also be used for display applications, so optimizing the emission of your pixels for lighting, and also metrology and defect. So I want to go over some of these applications in the next few slides, starting with the peak side, so the photonic integrated circuits. So the first thing when you talk about peak and photonic integrated circuit is we need to talk about the building blocks that we need to be able to build a photonic integrated circuit. And the first building block that we have is simply the waveguide. The waveguide, without waveguide, you don't have any photonic integrated circuit. So the equivalent of the wires on your electronic circuit. So for the waveguides, we have the capabilities to calculate the modes that can propagate in a waveguide, and we see an example here, the ACM picture of a waveguide with a cross section, and here what would be the simulation of a waveguide. So in this case, we have something that is probably a typical silicon waveguide with a width of 500 nanometer and a height of 220 nanometer. And this waveguide supports two modes. We have the transverse electric TE mode and the TM mode with different mode profiles. So a tool like Mode can calculate these properties of these waveguides. And then the other thing we need to know is that if we look at how the light is propagating in your waveguide. So in an electronic circuit, we don't really care if there's a 90-degree angle in your cable because the electrons won't have any problem with that. But you see that if we would do that with a waveguide, we would lose most of the light, and most of it would be reflected or lost. So we have to be able to model a band waveguide and calculate what are, for instance, the losses due to these bands as a function of the radius, for instance. And these are the kind of things we can do with the FDE solver. We can analyze straight waveguides as well as band waveguides. So the waveguide is one building block that is very important. And then here we have other type of building blocks. So I will start with these ones that are like the passive components. So we have this wide branch, and the idea of this wide branch is simply to split the light from one waveguide to two waveguides. And ideally what we want is a 50-50% ratio at each output here. And that can be done using FDTD or the VIA FDTD solver. Another type of component that is widely used in peak applications would be ring resonators. So ring resonators are simply filters that can be used like speckle filters. So we have an input waveguide and a ring, and the light from the waveguide will simply couple with the ring, and it will couple back and forth from the top waveguide to the bottom waveguide. And the ratio of coupling will depend on the wavelength of the light at the input. So again, that's something we can model with FDT or the VIA FDT solver. Or we can even split that in different bits, like the directional coupler, where the light is coupling from that waveguide, the straight waveguide to the band, and so on to build this structure. So those are two important devices. And then other type of device that we need in photonic circuit is couplers, like these grading couplers. The idea is that you need to be able to couple the light from, let's say, a fiber to the photonics chip that you have designed, and grading couplers are a great way to deal with that. So we see the top view of that. So simply we have the light propagating there, the grating there, and the light will couple in the grating, and you will see it start to propagate along the waveguide over here. And using an FDTD simulation, we can calculate the coupling and optimize this coupling, optimize the grating to get the maximum coupling possible. So those are passive components. So we only deal with the physics behind these components. And then we have the active components, as I talked about when I was introducing the different solvers that NC Merkle provides. One big, I would say, very important building block in photonic integrated circuits will be electro-optic modulators. So I think in this case, it's a bit misleading in a sense that we are not modulating light with this device. So here we have what I talked about, which is simply a waveguide where we use different dopings to create a PN junction over the waveguide. And when we apply a bias voltage on the electrodes on the sides here, we change the charge distribution over this waveguide. And this charge distribution simply will affect the optical properties of the waveguide. And we can then calculate using the charge solver and the FDE solver how the optical properties of the waveguide changes as a function of the bias voltage. And this will translate in your circuit with two different things. One is a phase shift, and the other one is additional losses due to the charge distribution. And those are the two data that we want to extract. And by creating a waveguide or part of a waveguide that can change the phase along its propagation, we can actually create an interferometer, and that will allow us to modulate the light. So we have a Mach-Zehnder interferometer where we split the light using, for instance, this Y branch, and on each arm of this interferometer, we control the phase and the phase difference between the two arms, meaning that by controlling the phase difference between the two arms and using another Y branch to combine both arms at the other side, we can control the amplitude of the light at the output of this device, and that will be our electro-optic modulator. And we also can thermally tune these waveguides. So the idea is exactly the same as here, except that we are not using dopings and charge distribution to control the phase and losses in this waveguide, but we're using temperature. So we have a heater where we inject a certain amount of power, and calculating the temperature using the heat transfer solver, we can then calculate how the optical properties of the waveguide are affected by the power that we inject in a heater. And that can be used to tune your system and to adjust your system based on the environmental conditions. Lastly, another very important component that you need to, or you may have to use in your photonic circuit will be photodetectors. Photodetectors, there's multiple things that we want to know. We want to know the dark current. We want to know the sensitivity, and these can be obtained from optoelectronic simulations. So for the dark current, we can simply do the simulation of this, the electrical simulation of the device using charge without any stimulus. But for the sensitivity, we need the combination of the optical and the electronic simulation. So on the optical side, we have like a view of this vertical photodetector. We have a waveguide, a taper that will allow to widen the mode propagating in this waveguide, and then we have a germanium layer that will absorb light and generate the photocurrents. So in the FDTD simulation, we will do this part where we can calculate what is the absorption in this germanium layer and see how, and from this absorption, we can then input that as an optical stimulus in the charge simulation to get the photocurrents. And we can also do some analysis to get the bandwidth of this device. Since I actually forgot to talk about that, but the charge transport solver can do steady state analysis, but also transient and small signal AC analysis that will allow you to get the bandwidth of the device. So for passive components, one key thing is how we can optimize the performance of your device. So we have multiple tools that allow you to optimize the devices. One tools that we added with the automation API is the inverse design module, or LUMOPT, that is using the Huygens method to optimize the figure of merit. In this case, the coupling efficiency to the selected modes of your waveguides. So the inverse design can work in two different ways. The first way is the parametric shape optimization. So here, what we are going to optimize, what we will optimize, is the shape of this Y branch. So you see, at each iteration, we generate a new shape and we calculate the figure of merit. And using the adjoint method, we simply can optimize fairly quickly this device and get about 100% transmission, knowing that here we are using the transmission in both waveguides. and we're using symmetric boundary conditions. So we know that the transmission is equally split between the two waveguides. So that's one way to work. And the other way is using the topology optimization. And in this case, the work is completely different. What you optimize is not the shape of the device, but it is the index profile in a section, a portion of your simulation. So we define a block, and at first, what we're going to do is simply vary the index in a matrix of basically like a matrix of pixel, and for each pixels, the refractive index can vary between two bounds. One will be the minimum value is typically the index of the clad, and the max value will be the index of the waveguide. So the first step is like a continuous variation where each pixels can take any kind of value, and then we need to discretize that because you can't really manufacture a device where there's like a continuous variation of the index. So we discretize that to get a step index type of profile. And so we applied this to this 1 to 4 wavelength demultiplexer with a 10 nanometer passband at these different wavelengths, and enforcing a 100 nanometer feature size constraint to make sure that the final device will be manufacturable. And you see in this animation simply how it works. We have first least continuous variation, and then after some iterations, we start the discretization process, and you see that the variation gets steeper and steeper up to the point where we have something that is almost or like a step index type of profile. And this gives us pretty good results. So we have the transmission spectrum at each of these different waveguides. And we can also show the fields as they propagate based on the wavelength. And we see that for each of these wavelengths, we have the outputs at the corresponding waveguides. So that's one way to optimize your structure. And that works very well for passive components. But in some workflows, it's actually it's much more complicated. And I talked about this electro-optical modulator or phase shifter, and that we can do with charge and mode. But optimizing these kind of devices can be a bit more complex than just an electro-optic simulation. And here we have an example that we showed a few weeks ago in Simulation World, this online conference that ANSYS hosted. And in this case, we are talking about a multiphysics simulation workflow, but also a multi-tool where we use numerical tools, HFSS also from ANSYS, and all the simulation workflow is driven using OptiSlang. So the workflow in this simulation is similar to what I talked about a bit earlier. So we have the charge and FDE simulation to calculate how the optical properties of the mode change with the bias voltage that you apply on that device. But also the charge simulation can help to extract the resistivity and the capacitance of this PN junction. And then in order to optimize the behavior of this device, we are using a traveling wave electrode. And this traveling wave electrode is optimized and designed using HFSS. The idea is to control the RF group index and so on to minimize the group delay between the mode propagating, the optical mode propagating in the waveguides and the electrical mode propagating in the electrodes. And all of these three different sides of the simulation workflow are used to create a traveling wave Mach-Zehnder modulator that can then be used in interconnects. And as I said, we have these basically 3 different solvers in 3 different packages, and the whole simulation workflow is driven in OptiSlang to optimize and get the best performance of this phase shifter in this Mach-Zehnder configuration. So that's for the component level side, and then we can actually step back and look at a broader view of this simulation workflow. And here we're looking at a full link where we go from let's say one computer to another using a fiber optic link that is like a few kilometers. And so we go from the PCB to the photonic circuit, the fiber, and then back to another photonic circuit, and then back to the PCB as well. And this is a view of the circuit in interconnect. And we have different things. So we have the transceiver side, where we have a bit sequence, we have optical sources, and we use all this to modulate the light, convert this bit sequence in an optical signal that is then sent to the fiber. So what are these different components? So we have the PCB here, where we convert the bit sequence into an electrical signal. And these have been simply simulated with HFSS, and we extracted the S parameters of the PCB to, from the bit sequence, get an accurate representation of the electrical signal that will be driving the photonic circuit. That is symbolized here. We have the traveling wave electrode that I talked about in the previous 2 slides ago. We have the optical modulator, or the phase shifter, and we have the Mach-Zehnder that I was talking about. We split the light here. We have the 2 arms of the Mach-Zehnder. We control the phase of each of each of the arms, and that allows us to modulate the light at the inputs of this modulator. And then we have the optical link, the fiber, and we have the receiver side, where we use photodetectors and current detection to extract the eye diagram of this circuit. So this can be used in this kind of transceiver, where we use complex modulation format like this PAM4 format, and we can extract things like I said, the eye diagram for the different bits level, and characterize the transceiver, calculating the beta rate, the signal to noise ratio, and so on. So another type of application that can be used, where photonic integrated circuit can be used, is for LiDAR. So as you probably know, nowadays, LiDARs are mostly fairly big devices where we steer the beam using a mechanical device. The idea behind this example, based on a paper that is shown, the reference is down here, is simply that we can use gratings and phased array gratings to steer the beam. So we know that if we have a grating like that, based on the wavelength, the width of the waveguide, the width of the corrugated side, and also the period of the grating, we know how the light will be coupled out of the grating. And we know that obviously these physical properties are fixed, but we know that if we vary the wavelength over this the input wavelength in this grating, we know that the output beam out of this grating, the angle will change with the wavelength. So that allows to steer the beam in one direction. And then what we can do is, instead of using one grating, we're using an array of gratings where we control the amplitude and the phase difference between each of these gratings. And by doing so, what we can do is, so we have the wavelength that can control can steer the beam in one direction, and by using this phased array, we can control the beam in the other direction, as shown in this little animation. And so we can use this type of device for the emitting side and also for the receiving side. And the idea is that we have a laser source where the wavelength changes as a function of time, and it means that we can use some current detection where at a single time t, we have the beam sent at certain direction, and by the time the beam is sent back, or the signal is sent back from the target object to the receiver side, we have a wavelength difference between the reference beam and the detected beam that allows us to calculate the time of flight and then the distance between the object and the LiDAR. So this is another way to use photonic integrated circuits in a very different type of application. So other type of application where we can use photonic integrated circuits will be sensing and lab on a chip, for instance. So here we have simply a photonic circuit where symbolized here, and what we use here is simply that we can if we change the optical properties of the material that is surrounding, that is close to the waveguide, it will change the properties of that waveguide. It change the refractive index and the effective index of the mode of that waveguide. And so in this application, what we do is we simply run an optical simulation of the waveguide using the transverse magnetic mode of this waveguide, and we simply sweep over the refractive index of the material close to the waveguide and see how the effective index changes as a function of this surrounding refractive index. And then using a similar Mach-Zehnder interferometer configuration, we can show that simply if you change the properties, the material properties close to the waveguide, it will shift the transmission spectrum of this Mach-Zehnder. And this allows us to measure and to detect materials surrounding the waveguide, and using that type of circuit as a sensor for biological application. Another type of sensor they could use is not really for photonic circuits, would be to use gratings. In this case, we have grating. We know that the transmission of this grating will be affected by similarly to this one, will be affected by the effective index or the refractive index of the material surrounding that. And so by monitoring how the reflection and transmission coefficients of this grating are affected by the surrounding index, we can know if like a material is present or not in nearby the grating. So that's about it for the photonic integrated circuit side. And now I want you to go over quickly, because I'm kind of running a bit late-ish, over some of the applications that I mentioned before. For instance, we have the CMOS image sensor that can be used, actually widely used in your mobile phone camera, for instance. And what you can do with the numerical tools is simply you can optimize the pixels, and to kind of avoid crosstalk and so on, optimize the absorption and so on. So we see SEM cross section of the pixels. We have micro lenses, we have color filters, different layers, different metallic bias, and then we have the absorbing region that we are interested in. And a top view, we have a full pixel that is made of 4 subpixels with different color filters for green, blue, and red colors. And we can then look at here how the light is absorbed by the green pixel. And we see that so the light is focused by the microlens, goes through the filter, and then can be diffracted by different elements. And we can see that, or we could see if the pixel was not nicely designed, that there could be some crosstalk and light diffracted from the green pixel to the red pixel, and creating some weird effects. And so the full optical part of this simulation workflow can be done with FDTD. So we can optimize the optical efficiency of the matrix and extract the generation rate, basically the absorption, and considering that each photon that is absorbed will generate an electron-hole pair, we can use that as a charge source in a charge transport solver. So in this workflow, we do things slightly differently. So we could use simply the absorption in this silicon layer to extract the photocurrents and the internal quantum efficiency of these pixels. But the way we do that is we cannot decouple the photonic side of the simulation and the electronic side of the simulation, simply because for one configuration, so we can, if you change, let's say, the microlens or the filters, this won't change the electrical behavior of your device, since the bias will be at the same place. The layers are the same. So what we do is, with one specific electronic configuration, we will calculate a weighting function, basically using a point generation source. We move that source all over the device, and for each position, we can know what is the probability of an electron hole pair generated at that position to be collected by this photodetector. So once we have that, we have a map showing the probability of an electron hole pair to be absorbed. We can use that and combine the absorption from the photonic simulation that will depend on the optical configuration, and combine that with this weighting function to extract the internal quantum efficiency of that device. So another type, completely different type of application, will be for augmented and virtual reality. It is meta-lens design. So in meta-lenses, what we do is we have this unit cell, which is a simple cylinder, and we can vary the radius and the height of these cylinders to control the phase and the transmission of that. The idea here is by appropriately distributing these cylinders with the right radius and height, we can control the phase of the light as shown in his animation. We eliminate with a plane wave, and we see how this device will affect the phase fronts of the light. And so this simulation workflow will start with a lot of simulations of these unit cells, where we calculate the phase change and the transmission. And knowing that, and knowing what is the target phase distribution, in this case we are targeting this hyperbolic lens, we can extract what would be the distribution of radius and height for this meta-lens, and then calculate the full the full behavior, the full meta-lens. Obviously, that would be a bit challenging in terms of simulation size, but then we can calculate what is, let's say, check the focal distance and so on. So another kind of applications where our tools can be used, like FDTD, will be for display, and in this case, we're using liquid crystals to steer the beam in our device. So we see the photonic crystal itself. We use a Gaussian beam, and we specially modulate the orientation of the crystals, and this allows us to control the direction of the output beam. And you see that the beam is now with an angle, and this can be done using FDTD and the anisotropic capabilities that we have, when we can modulate the full tensor for the permittivity. Another application that I mentioned, mostly for the interoperability between ray tracing and the photonic side, will be for lighting and organic LEDs, for like organic LEDs or LEDs. In this case, the main things we are interested in will be the emission pattern of that LED or LED, and that can be then used to build a full matrix and a full display. And so either you can consider your emitting structure simply as a system of multiple layers stacked together, and you know the thickness of each of these materials, the material properties, and so on, and we have the emission of this material on one specific layers, and we can use the stacked optical solver to extract this emission diagram and all the different characteristics of these layers. Or if your emitting structure has a limited size, and that is about the same scale of the wavelength, then you can use FDTD to do the same type of simulation, except that in this case it will be a bit slower, in the sense that we have to run full 3D simulations, and we also need to run multiple simulations in order to fully characterize the emission pattern of that LED. And then, as I said earlier, we can use these FDTD or stack simulation results to build a full display in a tool like Speos. And the last application that I will briefly talk about will be for optical metrology and defect detection. The idea behind this workflow is simply that we can decouple the optical system for the elimination and the collection from the actual FDTD simulation. So what we do is we will run a series of simulations with FDTD where we will simply change the incidence angle, and so basically we simulate the response of the system, the reflection of the system for all the angles that are supported by the optical system, and then we apply the illumination and collection path as post-processing, which means that we can actually for one set of simulations with FDTD, we can change the illumination and collection properties and try to optimize that separately, which will be much faster than try to model the full system for your needs. So yeah, that's about it. Thanks a lot for your attention. I hope I didn't bore you to death. If you want more information, we have a lot of information on our website. So all our documentation and application examples can be found at support.lecumerical.com. You can have access to a free 30-day trial version of our tools from our website, and feel free to contact Michel and his colleagues if you want more information about our tools and so on. And if there's any more questions that remain, well, I'd be happy to answer them.
Thank you very much, Greg, for your presentation. It was very good. Yeah, as Greg said, we are now open for question and answer. And meanwhile, we will send you in the chat the questionnaire. So feel free to fill it. It's like for 20 seconds. So we really appreciate the effort. So does anyone have a question to Greg? I mean, I see that there are a lot of academic people, so they always have a question. So feel free to put one. So anyone? Maybe I can have a question.
Yeah.
I mean, as I said at the beginning, so we are supporting ANSYS Speos in Czechia and Slovakia. So my question is if your software can be connected to ANSYS Speos to have some benefits, or it's still divided somehow?
No, there can be some connections. Actually, I mentioned that in one of the slides. So it's still a work in progress at this point, and it's mostly through file exchange. So we do the characterization with FDTD or any of our tools, and we extract some results. For instance, the coding emission transmission and reflection spectrum from FDTD, and use that, import that into Speos. And so we have these different examples that we already have like a proof of concept. We show them in an example. The next step for us, obviously, is to cover more applications. Like so, I said, we have these three. So the plasmonic, the reflection for coatings, the emissive structures for display, and the image sensors for camera simulations. So those are already available as example, and I think we have them on a website. The next step is to address these other applications, but also to do something that is a bit more, you say that, integrated in a sense that we're working on a plugging system where instead of having to extract like text file or MATLAB file and import that into Speos, we can have like a direct link between the two. But that will be probably for the next step, like next year or something like that.
I see. Thank you very much. I know you mentioned. I know that we have already had some requests regarding these diffractive optical elements for the headlamp producers, right? So there could be a big topic for them. So therefore, I want to like understand better how it's connected nowadays, and if there are some plans to connect in the future, which I like on the ANSYS the most, is that you don't need to really do some scripting these things in the future, of course, because LumiGrace is just acquired, right? But I see that there will be like a smooth process in a while that the customers can get benefit and really do some programming or buying some third-party tools also.
Yeah, I mean, there's different things we think of, and like another example is with OptiSlang, because OptiSlang has very powerful optimization algorithm that can be used to drive the simulation flow, and so this is a work in progress. I think the OptiSlang interoperability will be available with the 2021 R2 release next month, and so users will be able to kind of start playing with that. And I played a bit with it. Obviously, I have no experience with OptiSlang, so it makes things a bit more difficult for me. But I definitely see a huge potential to facilitate the optimization of devices with these combination of different tools.
Yeah, I mean that's valid definitely for all the portfolio of ANSYS, as we already had like talks also about the ANSYS spells. Cooperation with OptiSlang to optimize the workflows of our clients. So I'm happy to hear that it will be also possible with numerical programs.
Absolutely. I'm just seeing there's a few questions in the chats. I will need your help because I think some might not be in the right language for me. I can just reply to the two that are in English. So in terms of the wavelength energy, simply our tools are primarily meant for the photonics applications. At the end, the physics is the same as long as we're talking about electromagnetic wave propagating in a structure. Technically, FDTD could be used for that because we simply solve the Maxwell's equation. There's no assumption or approximation on on that. The one thing though is that because we come from the photonics world, it means that in FDTD or optical tools, we have a library of components, and the properties of these components, like the permittivity or the refractive index, might not be defined in these region of interest, like X-ray or so on. So in this case, what you would have to do is simply to have the import the properties of your materials at the desired wavelength and frequency. So that said, on the electromagnetic side, I don't think there's any limitation. But then if there's like interaction that are not that cannot be described by the Maxwell's equation, if we're talking about like quantum interactions, absorption kind of things, emission, that we cannot simulate that directly. There may be some other things we can do, but anything that can only be described by like a quantum effect or something like that, that's something we couldn't be able to model. Okay, and then there's this other question regarding plasmonic. Yeah, that's a typical application where FDTD had been used or have been used for years. So with the challenge that with plasmonic structures, the mesh size can be very critical, simply because we have metal objects, so metal to dielectric interfaces, and we need to first be able to resolve these interfaces accurately, but also we have huge fields variation from one side to the other of the interface, and that requires a fine mesh with FDTD to model those. That's a bit of a reason why we developed the DGTD solver in the multiphysical environment. DGTD stands for discontinuous Galerkin time domain, and so it's a finite element solver, which means that it's easier to mesh complex geometries that are not just planar or rectangular, but also it can deal with discontinuous fields at interfaces. So it means that in that sense, DGTD can be very interesting for plasmonic structure. Unfortunately for us, DGTD is a much more recent solver in our portfolio. In that sense, it's probably not as mature as FDTD can be, and there's probably a bit of features that are lacking. So I think depending on exactly what you want to model, we can definitely we may be able to use DGTD, but I would say FDTD can be used with the constraint that I mentioned.
Perfect. Thank you for your answer. I mean, the rest is in Czech, and those are regarding the questionnaire I asked the participants to fill. So yeah, just 2 questions, and you already reply. And I also want to mention to the participants that yeah, TechSoup is here to grab your question, and we will play with that together with Greg, and we will try to respond if you are interested in any particular program, let's say. So we would be more than happy to follow up on the cases you may have facing in your daily work, and also for the future projects, right? So you please free to contact us.
Absolutely.
So any other question? Maybe no. So I would like to thank you again for today, for your participation today. Feel free to fill the question mark also after the meeting, so it's still in the chat, so you can have a link and put your answers there. So we will be happy and follow in case you are interested in something specific, or you can write us an email so you can find all details on our web pages. And I also want to thanks Greg for his participation today. It was really very good for me, and I'm happy that I better understand the products that Ansys just acquired, and I'm happy to invest in the technical knowledge of my team to be able to handle questions of our clients for the future. So I'm looking very forward our cooperation in the future. And in the case of any questions, so feel free to reach us. Thank you very much for today.
Yeah, thanks a lot, and thanks a lot, Michal, and your colleagues for organizing this webinar. It was very nice for us. Thank you.
Thank you. Okay, so with that, thank you very much, and enjoy your lunch probably. And I'm happy to meet you for our next webinars. And as I said, feel free to reach us in the case of any question requirements or anything. Thank you very much, and take care. Bye-bye.
Bye-bye.
Bye.